But we're going to cover whatever we left off from the previous lecture, and then we're going to go into branch prediction today. Superscalar execution is an easy concept, so hopefully we won't spend a lot of time on it. But recall that you should be doing some readings. Hopefully everybody has read these, and hopefully everybody has read that one also, because we're going to talk about that today. And basically, we were done with everything until here, out-of-order execution so far. Today, we're going to briefly cover other execution paradigms, very briefly, and then we're going to go into branch prediction, and then we're going to cover more execution paradigms after we come back from the break. Let me see. Okay. So recall, this is a slide that you saw before. Basically, we talked about out-of-order execution being restricted data flow. And we can see that by being able to reverse engineer the data flow graph of a program by just looking at the state of the reservation stations, right? And the register file. You know that very well. You can reverse engineer the data flow graph, a limited part of the data flow graph. And the data flow graph that an out-of-order execution engine builds is limited to the instruction window, which is basically the instructions that are all decoded, but not yet retired. So you already know these concepts well. And we know that there's a reorder buffer. Reorder buffer keeps all of the instructions that are decoded, but not yet retired, right? Because when you decode an instruction, you put it in the instruction window. You take an instruction out of the instruction window when it's the oldest in the machine and it's done execution. Okay, we also discussed that. Can we do this for the whole program? How large instruction window can we have? We discussed that you do this for tolerating latencies if an instruction takes 500 cycles. And if you're fetching one instruction per cycle, then you need an instruction window of 500 entries if you would like to keep decoding, basically, instructions. And we also discussed that it's not very efficient because if you really want to, that whole wake up and select loop requires broadcasting the tag to all of the parts of the machine where you need to wake up instructions, and that could be a lot of places. And we also talked about the complexity of load store scheduling when you have out-of-order execution, because now a load, a store, a younger load may be ready to get scheduled, but there may be an unknown address store. So we talked about all of these different complexities. We didn't go into a lot of detail into load, in terms of load store, but I told you that that's really the most complex part of an out-of-order execution engine. Okay, and we went through this exercise. Hopefully you've done it yourself also. By just looking at this, you can construct the data flow graph. And I did it mostly for you, but you can finish it on your own. So let's talk about other approaches to instruction level concurrency. So we're basically making things higher performance, right, as we go along. So we did pipelining, we did out-of-order execution. So there are a lot of issues related to it. They give you high performance, but it comes at the cost of complexity and power consumption, which we didn't really fully talk about, but you can imagine the power consumption of the load store checking logic being one of the highest in the execution core. So the rest of, at least part of the rest of this class, we'll talk about some of these paradigms. You've already seen fine-grained multi-threading. Frank actually talked about that. Maybe we'll talk about that more when we talk about graphics processing units, for example. But today we're going to cover just data flow a little bit more and superscalar execution. We've already seen data flow at the ISA level, but I want to cover that again to contrast it with out-of-order execution. Because out-of-order execution is really assuming a von Neumann control flow ISA, right, sequential ISA, but it's doing out-of-order dispatch of instructions internally. So it's getting part of the benefits of a data flow ISA, but it's not really exposing this data flow execution to the programmer. And that has really made all the difference. So what is data flow good at? It's really good at exploiting irregular parallelism. So we'll see later that there's parallelism that's regular. So for example, if you're processing an image, and if you want to do some operation to the image, for example, resize the image, zoom in, or zoom out, what do? You basically apply an operation to every single pixel in the image. And that's very regular. Basically, one way of zooming out is actually what you do is you average the pixels that are around you and the pixel that you're operating on, and basically apply that filter to all of the pixels in the image. That's very regular because you do the same operation on every single pixel. in the image. We'll build engines that actually take advantage of this regular parallelism. You apply the same operation on every single element of data. So for example, another example is actually searching for a word across many, many words, across a huge book, for example. That's relatively regular. What you can do is if you're searching for the keyword, I don't know, Zürich, inside a 10,000 page book, it's a regular operation in the sense that what you can do is you can divide the book, 10,000 page book, into 1,000 10-page chunks, and you can assign each 10-page chunk to a processor, and that processor actually does the search for Zürich in that 10 pages. So you can actually use 1,000 processors to parallelize this operation. That's very regular. It's a different kind of regularity, but it's, again, very regular. Dataflow is very good at handling irregular parallelism. Like, you don't know how to actually parallelize some code, but basically, you write the code, and internally, the out-of-order execution engine figures out which instructions are independent. Right? The programmer doesn't need to think here, at least in the sequential version, right, in the von Neumann model. But people have also developed Dataflow architectures like ISAs, right? So the key concepts are, we talked about this before, but availability of data determines the order of execution. And a Dataflow node fires when its sources are ready, and you represent the programs as Dataflow graphs of nodes. So that's the difference between out-of-order execution and Dataflow ISA. In the Dataflow ISA, you represent the program with graphs that have nodes and vertices. Whereas in out-of-order execution, you start with sequential code, and that gets executed in a Dataflow manner. So exactly because of this reason, Dataflow at the ISA level has not been very successful. Basically, people have built a lot of machines starting from the 1970s, 80s, 90s, and they've tried to actually have a Dataflow ISA. They were actually good machines, very, very interesting concepts, but they weren't successful because the programmers needed to change their mindset in programming completely. And maybe there weren't enough tools also that would aid them. So at the ISA level has not been successful. Not many people program with these Dataflow graphs. Whenever you're writing programs, you don't think about Dataflow graphs today, right? How many program with Dataflow graphs today? Okay, I don't see many. Now, there are some higher level programming languages where you do graphical programming. That's actually, they incorporate Dataflow concepts, but in the end, they get translated into sequential ISAs today. So there's an even higher level concept like programming, Dataflow at the programming level, not the ISA level. Okay, so this has not been successful because it really changes the way people program. So what has been really successful is hiding the data flow from the programmer. Basically, that's what out-of-order execution is. You do this data flow execution internally in the microarchitecture level, while giving the illusion to the programmer that everything is sequential, which is the von Neumann model. And that has been extremely successful. All modern processors do it. Like this thing is doing it right now. All modern high-performance processors, I should say. There are microcontrollers that don't do it, but they're very low performance to begin with. Okay, so out-of-order execution is the prime example of this. So let's go back to the pure data flow. Pure data flow is really ISA level. It has also advantages. Some of these advantages are maintained in out-of-order execution. As I said, it's very good at exploiting irregular parallelism. You look at this code, you may not be able to figure out what the parallelism is, but the fact that it's executed in a data flow manner, instructions go into the reservation stations and wait, and whenever their source operands are ready, they fire. You get this parallelism that you wouldn't otherwise be able to extract from the program as a programmer or as a compiler. So that's, if you want to exploit irregular parallelism, data flow is actually the paradigm to use. Because the reason is only real dependencies constrain processing. You don't have any other constraints, right? If you have a data flow graph and only the real dependencies. And as a result, if you're doing it at the ISA level, you can actually expose much larger amounts of parallelism than compared to the von Neumann model. Okay, so these are the big advantages, basically. These actually, you can enable a lot of parallelism. Now, if your parallelism is regular, data flow, like what I described to you, right? If you're operating on an image and doing the same operation on every single pixel, and you have 1 billion pixels, for some reason you have a huge image, You can still have a data flow graph to do that, but it won't be as efficient. So we'll see much more efficient architectures that exploit regular parallelism later on. When we talk about array processors, single instruction, multiple data engines, GPUs, they're much more efficient at this regular parallelism. But if your parallelism is irregular, there's no better way of doing that compared to Dataflow today, at least in a general purpose manner. So disadvantages, clearly there are disadvantages. If you actually expose Dataflow at the instruction set architecture level, you don't have precise state semantics anymore, right? Precise exceptions, we talked about that. It's important so that the programmer can, whenever something bad happens, for some reason there's a fault, there's an exception, you can easily say, okay, that happened at this instruction. But if you have data flow, it's very difficult because there is no control flow to begin with. By definition, you don't have this precise state. There is no sequential execution. So as a result, these machines, this is the reason why these machines have really not been successful that use data flow at the ISA level. They didn't really have precise exceptions. This is also the reason why out-of-order execution machines that didn't have precise exceptions were not successful. Basically, debugging is extremely difficult whenever you get a bug in your program or whenever you have some exceptional event coming in, you have a problem, basically, because you don't know where to start. You have this huge data flow graph, and somewhere in the middle of execution, this mess happened. How do you actually reconstruct the state? And interrupt and exception handling is also difficult because precise state is required for that, right? Okay, but there are some solutions to the interrupt exception handling, but it's very, very complicated, which we're not going to get into. So the second issue is very interesting. Basically, what people have found out when they built these machines is you have too much parallelism. So you build this machine to expose parallelism, but they have figured out that, remember the out-of-order execution logic. If you make it really huge, you can fit very large data flow graphs. But it turns out you really need to make it extremely large to be able to handle real-world codes. And people didn't have enough hardware budget or power budget at that time to be able to do all of that tag matching, search, and have enough space in what looks like reservation stations. So this is true not in an out-of-order machine, but a pure data flow machine, basically. You can expose a lot of parallelism with a huge data flow graph, and you need to have a machine that handles that parallelism. Because if you don't have enough buffering in your machine, now you have the problem that you cannot keep track of which instructions are ready. You cannot keep track of the source readiness of the instructions. As a result, you may not be able to actually build a correct machine, or you actually need to store this data flow graph somewhere else, maybe on a hard disk, for example, and then keep bringing it in so that you can figure out which instructions are ready, but that's a lot of overhead. So as a result, this didn't work too well. So what these machines introduced was they introduced parallelism control. So they had to limit the parallelism. If there were too many instructions in the machine, okay, you cannot fetch more instructions. Essentially, a stall, basically. So it's a very interesting problem to have, actually. It's a good problem to have, perhaps, because you're exposing so much parallelism. Yes?
Parallelism control as in having enough reservation stations and things like that all works out, or having like a third party which actually supervises.
So you could do it both ways, actually. Yeah. Usually people use a third party that ensures that, like a third component that ensures that you won't run into issues like deadlock, for example. Okay, so high bookkeeping overhead, we already talked about that, actually. This is a problem with out-of-order machines also, but if you actually want to build a pure data flow machine, you also, actually, if you look at the out-of-order machine, it's very similar to the pure data flow machine. You need to do tag matching and data storage in a data flow machine also. Okay, and there are a bunch of other disadvantages that are related to programming that we're not going to talk about over here. But if you're interested, I actually pointed you to a particular lecture that I gave, so you can actually watch that lecture. Okay, so I'm going to cover superscalar execution also, and then we're going to switch to branch prediction. So superscalar execution, I already gave you the concept, actually. It's basically fetching, issuing, decoding, executing multiple instructions per cycle. That's it, I said over here. You have a machine that just doesn't fetch one instruction per cycle, but it does multiple instructions per cycle. It could be 4 instructions per cycle. Some existing machines do 8 instructions per cycle, for example. Clearly, this increases your throughput, right? As opposed to finishing 1 instruction per cycle, you're finishing, hopefully, in the best case, 8 instructions per cycle. That's actually very powerful. So if somebody says n wide superscalar, that means n instructions per cycle. So you need to add the hardware resources for doing so, of course. So this increases, you can think of these as n pipelines, right? Operating in parallel. But they're not completely parallel because there are dependencies between the instructions that are fetched at the same time. So we're going to increase the complexity also. So basically, hardware needs to perform dependence checking between concurrently fetched instructions. So whenever you're decoding 4 instructions per cycle, you need to make sure that those instructions, the hardware needs to figure out the dependencies between those instructions so that even though you've decoded 4 instructions per cycle, one of them needs to wait for the previous one, right? So in a pipeline, you're doing dependency checking in a linear array. Now it's like a 2-dimensional array, right? You need to check for dependencies for instructions that are before you, and also you need to check for dependencies for instructions that are being concurrently executed. I'm going to show you an example of this in a little bit. So this increases complexity, clearly, but the benefit is you have multiple pipelines for different instructions and you can get higher throughput. So this is very important. Actually, the paper that I assigned you doesn't do justice. The title is The Microarchitecture of Superscalar Processors. It should really be the microarchitecture of out-of-order superscalar processors, because these are 2 completely orthogonal concepts. And so superscalar execution and out-of-order execution. And you can actually have combinations of all processors. You can have an in-order processor that doesn't do out-of-order execution internally. It could be scalar, meaning you could fetch only 1 instruction per cycle, or you could fetch 4 instructions per cycle. It can still be in order, right? If all of the instructions are independent, that's good. You can execute those instructions in parallel. If there's 1 instruction that is dependent, then you stall because it's in order. Intel Pentium, for example, the first Pentium was an in-order superscalar machine. Pentium Pro later on made it out-of-order superscalar. Okay, so you can also have out-of-order scalar. That means that you're executing instructions potentially out of order, but you're fetching only 1 instruction per cycle. Makes sense, right? We've seen it actually. The machine that we simulated was an out-of-order scalar machine, because we were not able to fetch multiple instructions per cycle. We were not able to decode multiple instructions per cycle at a given time. We were able to execute multiple instructions per cycle, send them to the functional units, but that's very different, right? That's because functional units were available. So if I ask you the question, if you're fetching only 1 instruction per cycle, what is the maximum throughput you can get from the machine? Yes, 1, exactly, right? Because you're fetching only 1, you cannot complete more than 1 in the end, and the maximum. If you're fetching 2, the maximum is 2. So in the end, you have to fetch more than 1 instruction per cycle to be able to truly have a throughput that's more than one instruction per cycle. Yes?
When you, if they are out of order, would they leave the 2 instructions get finished?
Yes, but your throughput will never exceed 1, because you're feeding only 1 instruction per cycle into the machine. Yes, at some point in the intermediate execution, you may need to have more functional units. In fact, you do need to have more functional units to exploit that. But yeah, you cannot finish more than 1. Okay. And also you can have an out-of-order superscalar machine that's basically out-of-order plus n instructions per cycle fetch. So this is one example, in-order superscalar processor example. I'm not going to go through this in detail, but you can see that we're fetching multiple instructions per cycle. You need to have registers that are large. It's, again, 2 instructions per cycle. You need to have 2 sets of registers to read and 2 sets of registers to write to. And again, 2 ALUs to execute the 2 instructions. It's a simple machine. And then 2 ports to memory if you really want to be able to complete 2 instructions per cycle, 2 memory operations per cycle, and then 2 write ports. So basically, we've pretty much doubled the resources on the machine, right, to be able to do this. Yes? It could be different, but in this case, it's just a pictorial example showing that it's identical. But you could have, for example, 4 different types of ALUs, and you need to duplicate them if you want to be able to execute 2 instructions per cycle. Okay, so the difficulty here is dependencies make it tricky to issue multiple instructions per cycle. Basically, if the 2 instructions that you're fetching have some dependency relationship, you need to stall the older one. So here, ideal IPC is 2, clearly. But let's take, so this is an example where the consecutive 2 instructions are independent of each other. So if you look at them over here, yes. Yeah. Say it again? No. Basically, what this is doing is that it's fetching two instructions and assuming that they're consecutive. But yes, if you really want to be able to fetch, so this goes into the branch prediction problem that we will see. If you really want to be able to fetch different locations that are not sequential, then you really need two ports. And people play a lot of tricks over there, which we're not going to get into. But that's a very good point. But we're exploiting the fact that instructions are sequential in this case. Okay, so if you actually look at this code, the two instructions that are issued or decoded in a given cycle, they're independent of each other, so it's great. There's no stall that needs to happen here, so you achieve the ideal IPC. So you basically are able to finish 6 instructions in 3 cycles. But if you look over here, if you have dependencies, then there's a problem. For example, ideally, you would like to be able to decode load and add at the same time, but this add clearly depends on the load result because of this T0. So basically, this add needs to stall. Now, this add and subtract, they don't have a dependency relationship, so this add and sub actually can go at the same time. This and depends on the sub, so it needs to potentially wait, although if you have forwarding, that's not a problem. And if you look over here, basically, we don't achieve the ideal IPC because this load needs to go by itself and the next instruction needs to wait. So the actual IPC goes down by a lot, 1.2. 6 instructions are issued in 5 cycles. Right. And you can examine this yourself. So dependencies are, I mean, you saw that dependencies affect processing and pipelining. Pipelining, if it's a linear array, basically pipelining is in the X dimension. And Superscalar is really on the Y dimension. You basically have multiple pipelines. Clearly, multiple pipelines also get affected by dependencies. So dependencies are a problem. Okay, so let's talk about the advantages and disadvantages of this quickly. Clearly, you're able to fetch n instructions per cycle, so you can complete, hopefully, n instructions per cycle, so you get higher throughput, higher instructions per cycle. That's good, and this is a very good way of achieving throughput in machines. But of course, it comes at cost. So all of the improvements that we're going to make to the machines comes at cost. Higher complexity for dependency checking. Actually, I didn't show you the dependency checking logic. It's very similar to the dependency checking logic that you really need to do in a pipeline, except you're doing it in the same cycle, right? If you're fetching 4 instructions per cycle, you need to basically figure out which instructions are dependent. So it's actually worse than the pipeline's instruction dependency checking because you need to do it very quickly. So within a pipeline stage. We didn't have that before. And also, if you build an out-of-order superscalar machine, renaming becomes more complex because you need to, as opposed to renaming 1 instruction per cycle, now we're going to rename 4 instructions per cycle, right? So you need to add all of the logic to be able to do that. And if you actually do the logic design, you'll see that it's a mess. It's really a tree of comparators. Because you really need to, for example, if you're decoding 4 instructions per cycle, the 4th instruction that you fetch can be dependent on the 3rd one. It can be dependent on the 2nd one. It can be dependent on the 1st one. So you really need to compare the source registers of the 4th instruction to the destination register of all of the previous instructions. So that turns out to be really a comparator tree. And as you increase the number of instructions that you fetch, that grows. So essentially, you need more hardware resources for dependency checking. You need more hardware resources for execution, these additional pipelines, and maybe even instruction memory if your instructions you have a lot of branches. Okay, so that's all I have on superscalar execution. Now you know the concept and the advantages and disadvantages, so we can switch to the next part of the lecture.